All right, so now that we have worked a little bit with exponential expressions or exponential graphs, let's look at why we would evaluate or what a log expression is to us. They relate to exponential expressions directly, or exponential graphs, in that let's see, y equals, let's work in base 10 to the x. Now, y equals 10 to the x, it would be pretty easy to solve if I had, for example, 10 to the x equals 10,000. You'd have a pretty easy time figuring out what x is. That's not always true in every base. Imagine if I had e to the x equals 439,162. It might be a little bit difficult for you to figure out what x is in this case. And logarithms are all about solving exponentials because logarithms are easier to manipulate and they happen to be the inverse graph to an exponential graph. So let's look at that a little bit more directly. If I were to graph this exponential up here, I don't know why that erased, let's put it back in, y equals 10 to the x, then I would definitely get a graph that crosses the y-axis at 1, and whenever I put in 1, I should get 10 out, right? The base, the point 1b would be on that graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it would be right up here. So I get this really steep exponential curve that looks like this. So we know that inverse, and I alluded a moment ago to the fact that logarithmic graphs are the inverse of exponential graphs. That being true, if I reflect this very fine line, that's the line y equals x, if I were to reflect across the x-axis, I would end up with I need some cues to help me get the right shape. There we go. So I would end up with a curve that looks like this lower part, and this would be the logarithmic curve of this graph. In fact, this would be the curve y equals log base 10, and I don't have to write the 10 if it's a common log, but log base 10 of x. Now I have something I can work with because logs are much more simple to calculate. Not easy. I chose the word simple on purpose. They can be hard, but they're much more simple to calculate than an exponential when you're dealing with, difficult and funky numbers. All right, so that's a quick overview. Now let's actually start working with some. So just as it's possible with a algebraic expression or an algebraic equation to convert between an algebraic equation to its inverse by reversing my x and my y, we're going to do the same thing with logs and exponentials, but there's just a little positional formula to follow. And I like to use p's and q's, not x's and y's, because so often x and y are in our actual equations and it can be harder to see. So I like to use the form I was looking at my other formula. P equals my base to the q power. So P equals my base to the q power. Well, that would be the exponential form here, where P is representing y in this case. My base 10 is the b, and x is represented by q. So to switch that into logarithmic form, it's just a matter of, and it works in both directions, it's just a matter of moving around the values by position. So the whole point of doing this is to get this variable, this x, out front. Now see, you can see when I've graphed the log, I have y equals log base x. It's hard to tell that this is actually the inverse of this. So when we use p, b, and q, it's easier. The whole point of working with a logarithm is to get this q out of the position of power, because it may be in the position of power, but we have no power to figure out what it is. So if I bring the q out front, then the inverse function is that q equals the log base b of the only thing left. So I'm trying to find q. That's the whole point, is to isolate q. My base is always part of my logarithm, and then p is the only thing left to write down. So if I'm working in the reverse order, say I have, and I'll use different variables just to show that it's positional. Suppose I had, in this case, a equals log base, I'm going to keep b because base is base, log base b of c. Well, now I have to say, if I wanted to work in the other direction, I would just say, well, I'm trying to find c, so let's isolate c by itself, and I'm going to switch to an exponential. So an exponential has a base raised to some power, it would have to be a. And so if you think it through what you're doing, it's easier than trying to memorize this formula, which can be daunting when you just try to commit it to memory. Okay, so I'm going to erase this because I'm happy with the one we have with the double-sided arrows. Well, let's start with an easy one so that you can see the workings of the conversion. Suppose I wanted to solve or find, I would say, I can say this. Suppose I wanted to know what would x have to be for 2 to the x to equal 16. Well, we know what this is, because 2, 4, 8, 16, 2 to the 4th power, right, x would equal 4, easy to figure out. But we're using this simple number to kind of see the relationship and how a log could make this easier with harder numbers. So I'm going to convert this to a logarithm and solve it over there. I know, I sort of solved it over here just to remind us, but I'm going to convert it to a logarithm and solve it over here. So I want to know, what does x equal? Well, x equals, this is positional, so x equals log base 2 of 16. Okay, granted, at this stage of the game you're not thinking, oh yeah, that's so much easier, I totally get that. But let me introduce a couple properties that make this easier to do. If I can get the base of the log and the base of this number to be the same, then I have a property that lets me solve it. Okay, I have two properties actually, but that's easy enough to do because I can take the log base 2. We already know that if I wrote 2 to the 4th power, 2 to the 4th power equals 16. I've now converted my base for my log and my base for my exponent to the same value. And now here are my two properties. The first property says that if I have a logarithm to any base and I have a n to the mth power, that I can take that m out front, and this equals m times the log base b of n. This I will refer to as the monkey out of the tree property. You can thank Professor Deborah Narang at University of Alaska. She put that in my head 1,000 years ago. She said some other student had put it in her head, and once you get it in there, you can't get it out. But it seems to work really well. I think the tree is because a log and a tree, they go together. But it just says that if you have a logarithm with a power, then you can bring the power out front and end up with the power times just the simple log. So that's our first property. And then the second property we'll use right here in a moment is that if you have, as we did intentionally, log base b of b, where you have the same base raised to like 1, right? That just equals 1. Because they're inverses of each other, they undo each other, right? We talked about these are inverse relationships. They undo each other, so if you have nothing else but the relationships, they're gone. And so we have these two properties we can work with. So let's do it. Let's pull the 4, right? The 4 is the monkey in this case. Let's pull the monkey out of the tree. And I have x equals 4 log base 2 of 2. But this just equals 4 times 1, which is just 4. And now look, that's exactly what we expected to get when we just knew what the answer was because it was easy. So that's two properties for working with logarithms. Much easier, and if we have ugly numbers, much easier than trying to figure it out in the exponential form. So before we move on, let's build up some understanding of a couple more properties. Let's expand this one a little bit and say if I have a log base b of b to the x, meaning anything here, or even if it's a variable here, whatever, log base b of b to the x, we saw up here that just means take the monkey out of the tree and then log base b of b is 1. So this whole thing would equal x. Another play on that same idea would be if I have some base b raised to the log base b of x. So now all I've done is switched the position, right? So instead of having a log raised to, making finger quotes, raised to the b, I now have b raised to the log base b of x. And the same thing holds true. B and log base b are inverses of each other, right? So the base b and log base b are inverses. They equal 1, and so together they equal x. So it doesn't matter which order you take those two inverses together, they will undo each other and equal 1. So last but not least, I think we'll take straight from the graph, and that's what is the log of log base b, so true for any base, of 1. Well, if we look here on our graph, if I'm looking at log base b of 1, what do I get out? Well, my output is 0, so that just equals 0. Okay, so now that we have that, let's play around a bit. So let's see if I can keep my properties visible. Okay, so let's do example 2. I think that's example 2. Let's find the value of log base 5 of 125. Now remember, we're just gonna play with logs, but what we're really trying to figure out from log base, let me back up a little bit and say it, 5 to the x equals 125. Of course, this is always easy enough for us to figure out using just our fingers and toes, but imagine that we didn't have a pretty base or a pretty output value. We would convert this to the logarithmic form of x is what we want to find, equals log base 5 is always the base, of 125. So we want to convert 125 to some value with a base of 5. So 5 to the 5, 25, 125, so 5 to the third power. Monkey out of the tree equals 1. So the whole thing equals 3. All right, so x equals 3. Now, let's do a little bit trickier one, seeing this same logic to work with. Let's do example 3. Find let me put it on the other side. 5 to the x equals 1 over 125. Oh, okay, kind of looks the same. Looks like something I might be able to figure out in my head, but that looks pretty tricky to me. But let's convert it to a log and see how easy it is to finish up. X equals 5 to the, that's not what I want. X equals log base 5 of 1 over 125. But using the same logic I used here, well, let's convert the log base 5 of 125 to the minus 1, right? Because we can just bring it right up into the numerator and make it to a -1. But we already said before that 125 is the same thing as 5 raised to the third power minus 1. So we have log base 5 of 5 to the minus 3. Take the monkey out of the tree, cancel the inverses, equals -3. All right, so let's do another example. This time I'm not going to start with the exponential form and convert it to the log form. I'm just going to go straight to the log form. So find the log of 14. Okay, well that means I want to find log base. Oh, notice I didn't write a base. That's because this is called the common log. Base 10 is the base. When we don't write a base, it's implied base 10. It's the common log. It's how many fingers and toes we have. So it's the logarithm we commonly use. We work in a 10-digit system as humans. And so when we're talking about the log base 10, we don't write it down just because it's the common log. So we just don't write it down. So log base 10, or the common log of 14, means I'm looking for something to the 10th power, so I can cancel the inverses. But I have to find that power, and I want 10 to the something power to equal 14. Well, it turns out logarithms aren't always super easy to find, and we have to turn to our calculator. So let me grab that real quick. So my calculator, and most of the Texas Instruments calculators that we use, don't have buttons for every log base. I have a button on mine for a log base 10 and a log base E. All I have is a common log or a log base E. And to make it even more complicated, I only have access on my screen to log base E, which is called the natural log. We'll look at that in a minute. But sometimes you'll have access through these extra buttons from the menus up here, but none of my drop-down menus have any log functions on them either. For me, I have to go to my catalog if I want a common log, and I've set it up to already be there. So the common log I can plug in of 14 is, now, this is another thing to know about your calculator. If you're set to do pretty print, all I got was another form of the exact same thing. And notice my calculator converted a log base 10 to a common, or excuse me, to a common log to a natural log. We're going to learn about that in the coming days. But in the meantime, all you need to know is that when you get something that looks more complicated than what you were hoping for with some decimal answer, your calculator, sometimes it's second function button, and sometimes it's the diamond. For mine, if I click diamond and enter, it'll just give me this exact same calculation, but it'll give it to me in decimal form. So in this case, I know that x, or the power that I needed, would have been 1.146. So that's the value of the common log of 14. Let's do one more example. As promised, it's going to be a natural log. So example 5, find the natural log of negative, well, let's do find the natural log of 7. All right, so ln is a shorthand. This just means log base E. So as I spoke of before, the common log, because humans have 10 fingers and toes, we tend to talk in tens, have 10 numerals in our numbering system. The base for nature is E, and so we say the natural log, or the ln, I think that's French for natural log, abbreviation. The ln, or the natural log of 7, is what we want to find. So we know on my calculator that I find that function, that button, by clicking, which button? It's a second function because it's gold. So I want the natural log of 7. Again, it just gave me the natural log of 7, meaning it can't be reduced to anything else. So I'm going to click for the decimal. 1.9459. Let's round 1.946. All right, one more last example. I think I promised you only 2 more before, and now I'm giving you another one. But this is the last one, I promise. Let's find the natural log of negative 1.2. Okay, negative 1.2. So I'm already set up in my natural log. So I'm just going to back up and put in negative 1.2. Close my paren, enter. What? Domain error. So your calculator may say false. If you're using a scientific, it's probably going to say false. Some cue that you've done something wrong, or you've asked for something crazy. And you have asked for something crazy, because if we go back to the graph, we can see that the log graph has an asymptote at 0, meaning that we're never allowed to choose a negative value. The log function doesn't exist in the negative x range, at least not on the real numbers. So we can say this equals no real solutions. Okay, that's logarithms, evaluating log expressions in a nutshell.